Block codes. Already we have seen linear block codes. What is linear block codes? If you take two words, you know why you by this time you must know what is data word. By this time you must know what is code word. By this time you must know what is redundant bit. Okay. So here if you see a data word of length 2 is given, a redundant bit of 1 has been added and we are getting a code word of size 3, right? So K is 2, R is 1 and N is 3. So if you see how many code words are there, 4 code words 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0. What is linear block code is, if you take any pair of two codes and if you are going to perform XOR, after performing XOR you are going to get a result. No, if that result is one of the code words means that is called as linear block code. Take any combination of two code words, do an XOR operation and your resulting value must belong to any one of the code word means that is linear block code. Here example I have taken, see, I have not taken 0, 0, 0 because if you're going to XOR any code word with 0, 0, 0, you're going to get the same code word. Okay, if you want, you can try that. So I'm not taking, so I have left that combination. I will take 0, 1, 1, see 0, 1, 1 this code word and 1, 0, 1 I have taken. You perform XOR operation, 1, 1 means 0, 1, 0 means 1, 0, 1 means 1. See 1, 1, 0 is the result, no? You see, do you have a code word 1, 1, 0? Yes, I have a code word 1, 1, 0. Take another combination, take 0, 1, 1 and take 1, 1, 1, 0. Okay, two code words, two pairs I have taken. Do an XOR operation, 1, 0 is 1, 1, 1 is 0, 0, 1 is 1. Okay, what is your result? It is 1, 0, 1. Does it belong to any code word? Yes, we have a code word 1, 0, 1. Take the next combination. These two we have seen. Now take this combination 1, 0, 1 and 1, 1, 0 and do an XOR. 1, 0, 1 has been taken as one code word. The another code was 1, 1, 0. Do an XOR operation. 1, 0 is 1. 0, 1 is 1. 1, 1 means if both are same means we will get a value 0. Does the result belong to any of the code word 0, 1, 1? Yes, I have a code word 0, 1, 1. So this belongs to a linear block code. What is linear block code? Take any pair of code words and do an XOR operation. Your result, if your result belongs to the valid code words, then that is called as linear block code. Okay. So we have seen this table already. We have worked with this. You know what is Hamming distance? Hamming distance is if you take any two pairs and do an XOR operation and if you count the number of ones in your result, that is going to be Hamming distance. Okay. I can even see the Hamming distance for a single word. What is the Hamming distance for a single code word? It is the number of ones. If you take this, no, 0, 1, 1, the Hamming distance is 2 because how many ones are appearing? 2. If you take 1, 0, 1, what is the Hamming distance? How many non-zero values are there? Non-zero means 1. How many ones are there? 2. So the Hamming distance for this is 2. Take this code word 110. What is, how many ones are there? 2. So Hamming distance is 2. If you want to find the Hamming distance for any two pair, what you will do? Take two pair of code words, do an XOR operation. In the result, count the number of ones. Okay. Similarly, if you see, all codes which has been given here has a Hamming distance of 2. What is minimum Hamming distance? Out of all pairs of code, if you have worked with all pairs or individually if you have seen, find out of all the results you have got, out of all the Hamming values you have got, choose the one which is minimum. If I see everything is evaluates to 2, if you even if you XOR and see, that will be evaluating to 2. So out of that, which is the minimum value? 2 is the minimum value. That is called dmin. What is dmin for the given code words? It is 2. When you know the dmin value, you can tell how many errors the system can predict. If the dmin value is 2, how many errors, how many bit change it can predict? Dmin value minus 1. It can predict only 1 bit change. More than 1 bit, if 2 bit changes or 3 bit changes, it cannot detect. Okay. So if the minimum Hamming distance is given and if a question is asked how many errors the system can detect, what you will do? Hamming dmin minus 1 is the number of errors or bit change it can detect. Okay. So according to this, how many, since the Hamming distance dmin is going to be 2, 2 minus 1 is 1. So this system can predict only 1 bit error. Only if 1 bit changes, I will be able to say that Okay, something wrong has gone in my data. If 2-bit changes, I will not be able to detect that, because that is the capability of this system. How do we decide? Based upon the d-min value. If d-min value is 5, how many bit change it can detect? It can find out. D-min is 5, means 5 minus 1 is 4. So if 4 bit changes or 3 bit changes or 2 bit changes or 1 bit changes, it will be able to find it out. But if 5 bit changes, it cannot detect. If 6 bit changes, it cannot detect. So based upon the D-min value, you can say what is the capability of the system. Now this is simple parity check code. This also already we have seen. See here you have a data word of size 4. Okay, all 4-bit combination we have written. How many 4-bit combination you will have? 16. That's why we said how many data words will be there? 2 power k. 2 power 4 is 16. We are going to form a code word. What is the size of the code word? It is 5-bit. So how many redundant bit I have actually added? I have added only one redundant bit. That's why my resultant code word is of size 5. So k is 4 here, r is 1 and n is 5 here. Okay. So to the data word, to the k size data word, I have added a 1-bit redundant bit. So my resulting word is a 5-bit code word. Okay. Now take this. How did you form this code word using this data word? This is an even parity checker. Even parity means what? If you take any code word and if you count the number of ones, it must be even. That is called even parity. See, I will take this word. If I want to make it as even parity, if I add 1 here, will it become even parity? No, the number of 1 will become odd. So what I am supposed to add? I have to add a 0. That is what is given. Take this data word 0, 0, 0, 1. I want even parity. Even parity means how many ones must be there? Even number of ones. Already 1 is there. So if I want to make it as even number of 1, what is the next bit I have to add? If I add another 1 only, I will have 2 even number of ones. So add 1. Take this 0, 0, 1, 0. Count the number of ones available. 1, 1. Odd number of 1 is there. Actually, even parity means what? The number of ones must be even. So I must add one more bit, which is going to be 1. Then only even number of 1 will be. See, if you count the number of ones, what is there? So your redundant bit depends upon how many ones already exist. If odd number of 1 exists, I have to make my bit as 1. If even number of ones exist, I must make it as 0. Okay. So each data word maps to a code word. And we have already seen how many combination of code words will be the total combination. What is the size of the code word? 5 bits. So maximum how many 5 different combination, if you write, how many combinations you will have? 2 power 5. So 2 power 5 minus 2 power 4 will be the number of invalid codes. Okay, out of total codes, what is the total number of codes? 2 power 5. What is the total number of valid codes? 2 power 4. So what will be the invalid code? 2 power 5 minus 2 power 4 will be the resulting invalid codes available. And this is called as simple parity check code. And how do they represent? They represent it as C of 5 comma 4. That means what is your code word size? Code word size is 5. What is your data word size? Data word size is 4. What is the first parameter represent? N. What is the second parameter represent? K. So when N and K are given, you can easily say how many redundant bit. N minus K is your redundant bit. 5 minus 4 is 1. So number of redundant bit that has been added is going to be 1. Okay. Most of the system will be using even parity. Some system may use odd parity. If I want this to be an odd parity, if I am going to make use of an odd parity checker, then if I take this bit, the number of ones has to, if I take this word, the number of ones has to be odd. In that case, if I'm going to do an odd parity, I would have made, instead of 1, I would have kept a 0 here, right? So we need some components help in order to make this parity, no? So your data word, you have an encoder. What the encoder will do is, given the data word. In the previous example, what was the size of the data word? 4-bit, right? So A0, A1, A2, A3. LSB, this is LSB, this is MSB. So given a data word, you are giving it to a generator. What the generator is going to do? It will add one redundant bit, which we call it as a parity bit. In this case, the previous example which we saw was even parity. So I want to make it as even parity. According to that, I will decide whether 1 has to be added or 0 has to be added. After you add this, what is the size of the code word? Your data word size was 4. You added one redundant bit. Now your code word size is going to be 5. So this we call as R0 because this is redundant bit. Okay. And my data A0, A1, A2, A3 is okay. From here, the sender is going to send this information to the receiver. The receiver, just for identification, not to confuse, they have used B1, B0, B1, B2, B3 and Q0. Okay. The same data is going to come. But while the data comes, it may change or may not change. I have to find out whether the data has been changed, that is corrupted or not. So what they do, they give this to a checker. The checker is going to compute a syndrome. If the syndrome value is 0, that means no error has occurred. I can accept the data. How do I accept the data? This is not my whole data, right? I have to remove this redundant bit. So remove the redundant bit and accept your data. Suppose the checker, we are giving the result to the checker generates a syndrome. If the syndrome value is 1, that means what I have got is an errored information, that is corrupted data I have got. So I have to discard and ask the sender to resend. Clear? So given your code word, what the receiver will do, it will find the syndrome value. If the syndrome value is 0, my data has not been corrupted. I can accept the data. How will I accept? By removing the redundant bit, I will take the data. Suppose the syndrome which has been calculated results in 1, that means something has gone wrong in their data. Some bit has been corrupted. Okay. See here, what the generator will do is, it is going to XOR. Actually, if you XOR and see, you will know. If see, this is the data word which we are sending. An example has been given. Take the scenario now. Assume that the sender sends the data word 1011. What is the size of the data word? K. What is K here? K is 4. And what is the size of the code word? Code word is 5. So what is N? N is 5. Now I want to find out how many redundant bit has been added. If you check, compare this, you will know. But using the formula, if I want to find the redundant bit, how do I calculate R? R is nothing but N minus K. So 5 minus 4 is 1. So 1 redundant bit has been added. Okay. So the code word created from this data word is 10111. Is this even parity or odd parity? Count the number of ones. So number of ones is even. So even parity checker has been used, and based upon that 1 has been added, because this is the data word. Now count the number of ones. It is 3. 3 is odd. I have to make the number of ones as even. So I have added 1. If I add 1, the number of ones will become even. 4 ones are there. So 1 has been added. Okay. This is even parity. Using even parity checker, we have created our data word. Sorry, code word. Now this is sent to the receiver. We are taking 5 cases to find out whether error is detected or not. So now this is the code word which is being received. The receiver receives 1011. Yes, what I have sent has been received. How do I find that? I have to perform syndrome calculation. Syndrome calculation, what it will do? It will XOR. So XOR, first take 2 bits, 1 0. What will be your result? 1. Now 1 1. What will be your result? 1. Sorry, 1 1 is going to be 0. 0 1 is going to be 1. 1 1 is going to be 0. Right? Yes, XOR. You want to XOR. How many bits are there? What is your result? 1 0 1 1 1. This is your data, right? This is your data. You want to perform XOR. Take 2 bits and do XOR, no? First you take, I'm writing here. First is 1. After that I have 0. Okay, 1 0. 1 0. What is the result? 1 0 is going to be 1, right? 1 0 is going to result in 1 0 results in 1. Okay, I have taken this 1 and 0. Next bit is what? 1. This is my result. With this add 1. XOR 1 1 is what? 1 1 is going to be 1 1 is going to result in, now these 2 bits are taken, right? This was the result which I got from XORing 1 and 0. I have got 1. With that I am taking the next bit 1 and doing XOR. 1 1 is what? 0. Right? Now this is my result I have got. Now 3 bits has been added. Now 2 more bits are left. Now take the next bit. Next bit is 1. So 0 1 is what? 0 1. What is the result of 0 1? It is going to be 1. Right? So 1. Okay. Now, how many bits you have taken? 1, 0 is over. You have found out the result was 1. With that, you added the next one. The result was 0. With that, you added the next one. The result is 1. So, one more bit has to be added. What is 1, 1? It is going to be 0. So, the syndrome calculates to 0. The syndrome value calculates to 0. If the syndrome value calculates to 0, what it means? I have got the proper data, right? So, you have received the proper data. First case. First case, no error occurs. I have received it. How did the receiver found out that it has received correct data? It did a XOR on the available bits. So 1 XOR 0, XOR 1, XOR 1, XOR 1 resulted in 0. That is what I showed you now. So the data word, what is the data word from this? I know that 1 is redundant bit. Leave of the LSB. So the remaining 1011 is my data. The data word is created, right? Now we will assume that the same thing, this data word was sent and this data word was created into this code word and I am sending to the receiver. While it is being transmitted, now assume that A1, bit number A1 has changed. You know that this is R0, this is A0, this is A1. So this has been changed. What is the actual value? 1. It has been changed to 0. Now the receiver has got the result. It has to find whether the data is corrupted or not. Actually what happens? The data is corrupted. Now it is going to calculate the syndrome. How does it calculate the syndrome? By XORing. Take the first bit is 1, take the next bit is 0. 1 0, XOR 1 0, what is that? 1. Now your result is 1. Once again add it with, XOR it with 0. 1 0 is 1. XOR with this one, 1 1 is 0. XOR with this one, 0 1 is 1. So if you XOR the bits together, your final result is 1. You can easily say that if there are odd number of ones, we will get 1. If there are even number of ones, we will get a 0. Okay. So the syndrome value has been calculated to 1. The syndrome value is 0 means we have got the proper result. If the syndrome value is 1 means my data has been corrupted. So since the syndrome value is 1, it will not create the data word. It will discard the data word saying that something has gone wrong. So it will discard it. Okay. And third scenario has been given. One single bit error occurs. You are transmitting this data 10111. A single bit error occurs. That occurs in R0. R0 is this position, no? So this actually it was 1. It has changed to 0. Okay. The receiver has got instead of 10111, the receiver has got 10110. Now the receiver has to find out whether the data has been corrupted or not. It is going to calculate the syndrome. Calculate the syndrome. 3 ones means your final result will be 1. Odd number of ones means definitely the XOR. After XORing, you will get 1. The syndrome value is 1. Now, what it does, since the syndrome value is 1, it is going to neglect the data. Actually, if you see, your data has not been corrupted. Your data is 1011. That is your data, no? It is proper only. Which has been corrupted? The redundant bit. But in this system, we don't have provision to say, we don't have provision to check whether the data bit has been corrupted or the redundant bit is corrupted. If we have that provision, I can easily find out whether my data bit has corrupted or redundant bit has corrupted. At that time, I would have received this. Since that particular facility is not implemented in this, we are just the system will neglect the data saying that something has gone wrong. Okay, actually my data has not corrupted, only the redundant bit has changed. But since there is no facility to identify whether the change occurred in the redundant bit or the data bit, this is going to discard it based upon the value of the syndrome. Okay. Next, we will have another one. Fourth scenario. Assume that your R0 and A3 has been changed. Okay, you know this is R0, this is A0, A1, A2, A3. So R0 and A3 has been changed. See here 1 has been changed to 0. Here 1 has been changed to 0. Now this is what is received by the receiver. The receiver has to check whether it has received proper data or the data has been changed. How it is going to do? It has to calculate the syndrome value. Calculate the syndrome value. What you will have? 0 0 0 0 1 1 1 1 is 0, 0 0 is 0, right? Your result is going to be 0. So it says that when the syndrome value is 0, what it means? We say that no error has occurred. Actually, what happened? An error has occurred. See, 1 has been changed to 0, but the system says that no error has occurred. Actually, it is detecting wrongly. Why? Because the simple parity check decoder cannot detect even number of errors. So, what is the capability of a parity checker? Is single parity, simple parity checker is it can only detect one error or three error or 5 error. Only odd number of errors can be detected. That is the capability of the system. It cannot detect even number of bit change. Here how many bit change has occurred? 2 bit change. So actually it has to say that yes, the data is corrupted and discard. But since the syndrome value has resulted in 0, it is taking the data as a proper data. It is not the proper data. Why? Because this does not have capability to detect even number of errors. So, what is the capability of a simple parity checker? It can detect only odd number of bit changes. If one bit changes, it can identify. If three bit changes, it can identify. If five bit changes, it can identify. But if even number of bit changes, 2 bit changes, or 4 bit changes, or 6 bit changes, it will not be able to identify. Okay, the last scenario, see, 3 bits A1, A2, and A3 are changed. This is A1, this is A0, A1, A2, A3. So this bit has been changed. See, 1 changes to 0, 0 changes to 1, 1 changes to 0. Okay, this is the data received by the receiver. Now it has to calculate the syndrome. To calculate the syndrome, it will take all bits and find the XOR. So 3 ones are there. What will be the result? It will be 1. The syndrome results in 1. Whenever the syndrome value is 1, what is that? The data has been corrupted. So the data has been corrupted. It will neglect that. Here, how many bits have changed? 3 bits. Odd number of bit change it is able to detect, whereas even number of bit change it will not be able to detect. That is the capability of the system, right? So what we saw, the previous one which we saw is linear block codes, right? What is linear block codes? If you take any two block codes and of same size and you're going to perform XOR, and if your resulting block code belongs to the valid code words, then that is called linear block codes. One extra property is added to the linear block code, and that we call it as a cyclic code. Okay, what is that extra property? See, cyclic codes are special linear block codes with one extra property. What is that extra property? Is in a cyclic code, if a code word, you must know what is data word, you must know what is code word. So in a cyclic code, if a code word is cyclically shifted, that is rotated, that is you are doing a right rotation or a left rotation, the result must be another code word. The result must also be belong to one of the code word. That is going to be your cyclic codes. Cyclic code follows all the property of linear block code, plus it has one more extra property. It has to satisfy one more extra property. What is that? If you're cyclically, if you're going to rotate your code word, the resulting word must belong to the valid code words. For example, you take this has been taken. This is left shifter. Okay, 10, this has been taken. Okay, 1011 triple zero. See, we are performing a left shift. This 0 will come here, this 1 will have has to come to the right. We are doing a left shift, so this will come here, this 0 goes here, this 1 goes here, this 1 goes here, everything is moved by one position. The last position will be filled by this 1. Okay, this is the result. You see whether the result falls under valid code word. Do you have 011 triple 01? Yes, 0 0 1 1 triple 01. See, okay. Now take this example, 101100. The same example we are doing here. What shift we did? Left shift. I want to perform right shift and see whether it belongs to the same one of the code words. Do a right shift. So this will be shifted here. This 0 will come here, this 0 will come here, this 1 will come here, this 0 comes here, this 1 comes here. This position is vacant, that will be filled by this 0. So your result after doing a right shift, what is your result? 0 1 0 1 1 0 0. See whether you have somewhere in the code words, if you see 0 1 0 1 1 0. So After I do perform a shifting, either it may be right shift or left shift, but your result must belong to the category of valid code words. It has to lie in this group, any one of this group. Okay, so if it is so, that is called as what code? Cyclic code. Cyclic code satisfies linear code property plus one extra property is shifting will result in one of the code. Okay. So cyclic redundancy check. Okay. So cyclic redundancy CRC is a subset of cyclic code. There is a code called cyclic redundancy checker. Okay. That cyclic redundancy checker falls under the subcategory of cyclic code. Okay, by this time you must know what is cyclic code. So CRC is one of the cyclic code which will help us in error correction. So far what we saw was error detection. That system helped me in telling whether I have received correct data or not. Error detection. Here the CRC will help us not only detecting error, it will help us to correct that error and rectify or retrieve the proper data. Okay. So CRC is a subset of cyclic code and it helps us in error correction. Error correction means it can detect as well as correct. So how that is being done we will see. So CRC code with C of 7 comma 4. A code, see this is the data word. What is the size of the data word? It is 4. This is the code word. I will tell you how we are getting this code word. In the parity, simple parity checker, how did we get the code word? We added a parity bit. Okay, that bit values may be either 0 or 1. How do you decide that? By counting the number of ones. Final result has to contain even number of ones. Based upon that, it was added. Similarly, here how they are adding, I will tell you. So this is the data word. What is the size of the data word? K is 4. This is the resulting code word. What is the size of the code word? 7. N is equal to 7. So, if you know the n value and if you know the k value, you can tell me how many redundant bit has been added. How many redundant bit? 7 minus 4, 3 redundant bit has been added. Okay. How we are adding this redundant bit? How we are generating this code word? Using this data word, how we are arriving at this code word, I will show you. Here, they use a polynomial in order to generate this. In order to generate a CRC code, they use a polynomial. Your polynomial, a given string, your data string will be there and you will be given a divisor. That divisor is called as generator polynomial. Using the generator polynomial only, you will arrive at this code. This is your input, right? This is the data word. I want to arrive at this code word. To arrive at this code word, I need to do some division operation. For the division operation, I need a divisor. The divisor is called as generator polynomial. Given a data bit stream and given a divisor or a generator polynomial, I can arrive at this code word. Okay. So we will see an example how to arrive at the code word. Before that, we will see what does the encoder do, what does the decoder do. So your data is given here. We will assume 4-bit data. So he has given A0, A1, A2, A3. This is your data word. You are giving it to a generator. What it does, it adds parity bit. Okay, sorry, it adds redundant bit. How many redundant bit has been added? 3 redundant bit has been added to that and it is going to generate a code word. If you see code word size is what? 4 plus 3. So 3 redundant bit has been added. So total size becomes 7. So this is R0, R1, R2, A0, A1, A2, A3. So this is being sent to the receiver. The receiver takes this. Just for our understanding, A has been given as B here, R has been given as Q. Otherwise, we will have a confusion. So they have given like this. So the received code word is given to the checker. The checker is going to generate a syndrome. In the previous one, syndrome was a single bit, no? Here the syndrome will result in a 3-bit. So if all the 3 bits are going to be 0, then it means that your data is not corrupted. Whereas if the 3 bit, any 1 bit becomes 1 means, any 1 bit or all bit becomes 1 means, it is assumed that it is identified that the data has been corrupted. So your syndrome in this case is 3-bit. All 3 bits are 0 means my data is not corrupted. If any bit is going to change means, that means the data is corrupted. If you get a corrupted data, what you will do? You will just discard it. If you get a proper data, what you will do? Just remove that redundant bit Q0, Q1, Q2 and just take your data word. Okay, that is the job of the receiver. So encoder, here it is decoder. Now how to arrive at that code word? That is what we are going to see. Now this is your data. See, data is 1001. We will take, I will just show that in this table. See, 1001. It's there, no? 1001. Okay, 1001 we are taking. This is the data word, right? And they have given the generator polynomial. There will be standard polynomials which can be used for dividing. So the generator polynomial which we are going to use here is 1011. Okay, so what is the data I have taken? 1001. What is the generator polynomial or the divisor? 1011. Okay, without the divisor we cannot arrive at this. That's why divisor has been given. So you will work out this. So 1011 is your divisor. Your data is 1001. You have to add 3 zeros here. Why you have 3 zeros? It depends upon the length of your divisor. If the length of the divisor is 4 bit, you have to add 3 zeros. If your length of the divisor is 5 bit, you have to add 4 zero. If your length of the divisor is 6 bit, 6 minus 1, 5 zeros has to be added. Okay. How many zeros you will add? How many redundant bits you are going to add to your data? It depends upon the size of the divisor. If divisor size is m, you will add m minus 1 zeros here. Okay. So since the size of the divisor is 4 here, 4 minus 1 is 3. So 3 0 has been added to the data word. After adding it, this is the dividend. On this dividend only we are going to divide. Okay. So my divisor has been given, the data has been given. The data has been converted into dividend by adding 3 zeros. This number of zeros to be added depends upon your divisor. Just now I told you. Now we are going to divide. So if you have 1 here, apply 1 here. Okay. So 1 times 1 into 1 is 1. 0 into 1 is 0. 1 into 1 is 1. 1 into 1 is 1. Just forget this. What is your data? It is 100100. Okay. What is your divisor? Your divisor is what? 1011. Okay. How I am going to divide it? See, if there is a 1, we put it will go for 1 time. So I am putting a 1 here. My quotient is not at all important. Okay, 1. So multiply 1 times 1 into 1. Multiplication is AND operation, right? Subtraction or addition is or XOR operation. Multiplication will be AND operation. So this 1 into 1 is what? 1. 1 into 1 is 1, right? Next, 0 into 1 is 0. Next, 1 into 1 is 1. Next, 1 into 1 is 1. AND operation. Okay. Now find the subtract. You have to perform no division, normal division. What you will do? We'll find this difference. So subtraction or addition, for that in binary what we will do? We can do XOR. So perform XOR operation. Perform XOR operation. 1 1. What is 1 1? It is going to be 1 1 is 0, right? 1 1 is 0. What is 1 0? 1 0 is 1. What is 0 0? 0 0 is 0. Okay. So we perform XOR operation. See, 1 1 is 1 1 is 0, right? 0 1. If both are same means XOR operation 0, right? 0 1 means 1. 0 0 means 0. If both are same, 0. Okay. Now this you have got. This I am not writing. Usually we will neglect now. 1 1 is 0. Anyway, we are not using. Now I have to bring the 0 here. So I have to bring this 0 here, right? So what is the next bit? Next bit is 0. So I am adding this. Now with this I have to proceed. Okay. Now take this. Here 1 is there, here 0 is there. So it will go only 0 times because No, based upon the weightage, you can say this number is greater than this because the first bit is 0. I am not bothered. At least the first bit, if it is 1, we can multiply at least one time. When the first bit is 0, naturally we will know that this data is smaller than this. So in a lower data, this cannot go. So I am putting 0 here. So 0 into 1, everything will be what? 0, right? 0 into 1, 0. 0 into 0, 0. This 0 into 1 is 1. Multiply everything by 0 because we have added 0. 0 into 1 is 0. Everything is 0. Now once again what you do? Find the difference. Find the difference. Difference means we will perform XOR operation, right? So perform XOR operation. 0, 0 is 0, 0 is what? 0. So 0. 0, 0 is 0. 0, 1 is 1. Okay. So I'm neglecting the last one. So 1, 1, 0 is 1, 0, 0 is 0, 0, 0 is 0. Now take the next bit. The next bit is this. So I'm going to place it here. What is the value? That is 0. Okay. Now I have to find out. So since the first place is 1, I know that by seeing that we can say that this is smaller than this. But since 1 is appearing, we can multiply it with 1. Because our quotient is going to be wrong only, but we are not bothered about the quotient. We will be bothered only about the remainder. Okay. So 1. 1 times multiplying, what will be your result? It will be 1 into 1 is 1, 1 into 0 is 0, 1 into 1 is 1, 1 into 1 is 1. You will have this, right? Now find the difference. Difference means XOR operation. So what will be your result? What will be your result? 0, 1 is 1. 0, 1 is 1. 0, 0 is 0. So this is the result we are getting, right? So 0, 1 is 1, 0, 1 is 1, 0, 0 is 0. Still I have one more bit, no? That also you bring it and do the operation. Do the same manipulation. So what is that? I have to bring the 0 here. So I am placing the 0. Now I have to find, since this is 0, you know that naturally, see, 2 power 0, 1, 2, 4, 8. Naturally this will be greater than this. So only 0 times it will go. So 0 into this number, what you will have? Everything will be 0, no? So 0, 0, 0, 0. Find the difference now. Find the difference. What is the difference? 0, 0, XOR. Perform XOR operation. So 0, 0 is 0, 0 is 0, 0, 1 is 1, 1, 0 is 1, right? So 0, 0 is 0, 1, 0 is 1, 1, 0 is 1. So what is your reminder? Here it will come 0. Anyway, we are neglecting. So how many zeros we have added? 3 zeros. So last 3 only we are bothered. Even if there is a 0, we are going to neglect it. So what is the bit you have to add? What is the redundant bit you have to add with your data is? Your data is 10012. To that 1001 you are going to add 110. How did you arrive at this? You must be given a divisor. Already they have fixed certain polynomial as a divisor. For based upon each protocol, they have worked on that and they have decided this is going to be the divisor for this particular protocol. So based upon that, you will have the divisor. So given your data, you're going to given a data and your divisor, you can decide how to arrive at your code word. So how to arrive at the code word? If my divisor is 4-bit, I have to add 3 zeros. The length of the divisor minus 1 will be the number of zeros to be added. If my divisor is of length 5, I have to add 4 zeros. After adding it, perform a division. Once you perform the division, we are not bothered about the quotient. We are bothered only about the remainder. The remainder is your redundant bits to be added to your data. What is the remainder? 110. Actually 3 zeros we have added, no, only the 3 bit we have to take. So 110 that will be added with your data and this is your code word. If you see for 1001, if you see your table here, your table is here, no? For 1001, the code word will be this. See, 1001, what has been added? 110. Already they have given this table, right? But so to know how to arrive, I did it. I have taken another example also. But before that, we will see this. Okay. Now, you know what is being sent from the sender? It is 1001. To that we have added 110, and this code word is sent to the what? Receiver. Receiver has got the correct word. How will that know whether it has received the proper word? Once again, using the same divisor, it is going to divide it. See, 1 is there, so write 1 here. 1 times. What will be 1 times multiplied by this? 1011. See the difference. 1 into 1 XOR 1 is 0. 0 1 is 1. 0 0 is 0. I am not bothered about this. Anyway, it is going to come as 0. Now bring this 1 here. Your data is 0 1 0 1. So this bit is 0 means naturally this is lesser than this. So we are marking it as 0. 0 times of 1 0 1 1. What will be happen if you multiply every bit with 0? Everything will be 0, no? So 0 0 0 0. Find the difference. How do you find the difference? Using XOR. 1 0 is what? 1. 0 0 is what? 0. 1 0 is what? 1. Okay, this becomes 0. Anyway, we are taking this 1 0 1. Now bring the next bit. Next bit is 1. So here 1 appears, no? So 1 time we will use 1 time. 1 time of 1 0 1 1. Multiply with all bits by 1. What you will have? 1 0 1 1. So write 1 0 1 1. 1 time multiplied means that will be the same. 0 time multiplied means everything will be 0. Okay. So 1 0 1 1. Now find the difference between this. Subtract this from this. How do we do subtraction in binary? XOR. So perform XOR operation. 1 1 is both bits are same means 0. 1 1 both bits are same means 0. 0 0 both bits are same means 0. So everything has resulted in 0. Okay. So take the last 3 bits. This is your syndrome. Okay. Yes, not. S1, S2, whatever has been given there. Okay. So syndrome is 0. If the syndrome results in 0, what I said? No, nothing has been corrupted. So from this received word, how will you take your data? You know that 3 bit has been added extra. Remove that 3 bit. So your data is 1011. We will assume that a bit has been corrupted. Okay, 1 bit has been corrupted. See, actually what is the data you sent? 1001 So that is being received here. But see, this bit has been changed. Okay, instead of 1 it has changed to 0. We have to find out whether the system must be able to detect that error has occurred. Do the same division 1 time. 1011 you will get, right? Find the difference. 0 1 is 1. 0 1 is 1. 0 0 is 0. Bring this 1 here. Here 0 is there, no? So only 0 time. 0 time of 1 0 1 1. Multiply everything with 0, you will get all 0. So 0 0 0 0. Now find the difference between this and this. How do you find the difference? Using XOR operation. So 1 0 is 1. 1 0 is 1. 1 0 is 1. Okay? 3 ones. Now bring this 1 here. 4 1. See, since the last bit is 1, it will go 1 time. So put a 1 here. 1 into 1 0 1 1. What you will get? 1 0 1 1. So 1 0 1 1. Find the difference now. Difference we will do XOR operation. Multiplication we are doing AND operation. Subtraction we are doing XOR operation. So perform XOR 1 1. Both bits are same means 0. 1 1. Both bits are same means 0. 1 0. The value is 1. 1 1 is 0. We are not neglecting that. Okay. Now bring the 0 here. Now your data is 1 0 0 0. Since 1 here appears here, put 1 times. 1 time of this, what it will be? 1 0 1 1. So 1 0 1 1. Find the difference. That is for difference, what you do? XOR operation. 0 1 1. 0 1 1. 0 0 0. 1 1 0. But we are bothered about only 3 bits. This is your syndrome. Your syndrome, if your syndrome value is all 0, your data is not corrupted. If your syndrome value is not all 0, some bit has been changed means definitely your data has corrupted. Yes, this is a corrupted data because what did you send? 1001. But what happened here? 1000. It has changed. So the receiver will be able to detect. Since the syndrome value is not all 0, if the syndrome value is all 0, I have received correct data. I will accept it by removing the redundant bit added. Here, since the syndrome value is not all 0, it means that some error has occurred, so it will discard the data. So here another example I have done it for finding the code word. Same one. I have taken one code word from the table. This word has been taken. 1100 I have taken. and this is the divisor. So divisor length is 4 means you have to add 3 zeros. Once you do the division now, the remainder you're getting is 0, 0, 1, 0. How many bits we have to add to our data? 3 bits, right? 0, 1, 0. So that is added. After adding that, this is the code word. Okay, if you see, this is the code word for this 1, 0, which is that one? 1, 1, 0, 0, right? 1, 1, 0, 0. What is the code word added? See, 0, 1, 0. That is what we have calculated. So this is another example to just show how code words are added. You can take any code word and do it using this divisor, do and see, you have to arrive at this. If you take this code word, you have to arrive at this. If you take this code word, you have to arrive at this. Please do try and see. So with this, we will wind up.